Hello, everybody, and welcome to this 11th edition, 11th webinar as a part of the Sustainability Seminar Series organized by the Dr. Kiran C. Patel Center for Sustainable Development here at IIT Gandhinagar. My name is Jaychandar Swaminathan. I am an assistant professor in the Mechanical Engineering Department, and I'll be the moderator for today's session. It is my great pleasure to introduce our speaker, Ambassador V. Ashok. Ambassador Ashok is a graduate in civil engineering from IIT Delhi. He has held diplomatic assignments in Hong Kong, Malaysia, China, Austria, Sri Lanka, and the USA. He was India's ambassador to the Czech Republic and Zimbabwe and retired in the rank of Secretary Government of India. He is now a guest professor at IIT Gandhinagar and is an adjunct professor at IIT Bombay and NIAS Bengaluru. And he was also the 2018 Garwood Fellow at the University of California in Berkeley. He can speak Chinese and several Indian languages and has authored a book titled Dashavatara, the 10 Incarnations of Vishnu. So with that brief introduction, I'll hand over the floor to Ambassador Ashok to tell us about ensuring India's water security. Just a note to the audience, you can please use the Q&A button throughout the session to post your questions. Towards the end, we will collate these and then post them to the speaker. Thank you.
Thank you very much, Professor Jaychandar Swaminathan. I also wish to thank IIT Gandhinagar and the Kanchan Harilal Doshi Chair, which is Professor Jaychandar, at the Center for Sustainable Development, and Dr. Falguni Taylor, Project Manager, Kiran C. Patel Center for Sustainable Development, for hosting my webinar as part of the Sustainable Seminar Series at IIT Gandhinagar. My career has been as a diplomat in the Indian Foreign Service. However, I graduated as a civil engineer from IIT Delhi and have since retained a keen interest in science and engineering, including water management and sustainability. I hope to share with you all today my thoughts on water security for India. And I wish you all a very good afternoon or good day. To all participants, welcome, and thank you for sparing your time and joining us today. After my presentation, I welcome your questions and comments, which will follow. Thank you. Shall I continue with the presentation?
Yes, please go ahead.
Yeah. And this is an issue which is of very grave importance for India and the world. You may have heard the sayings that the future of the future petroleum will be water. And similarly, you may also have heard that future wars will be fought on water. For India, this is a very critical issue. And I wish to show this first slide to give you an idea of what I exactly am trying to imply. India is facing its worst water crisis in history. And this is something that the Niti Aayog has said, that the demand for water will outstrip supply by 2030 if steps are not taken to correct it. Bengaluru, Chennai, Delhi, Hyderabad, and in fact, several other cities are very susceptible to this. And Bengaluru, in fact, has been put on the zero water list, the Cape Town list, as it might be called. But the other cities are also not very far behind. And the World Resources Institute has ranked India 13th on its list of extremely highly water-stressed countries. India has more than 3 times the population of the other 16 countries in this category combined. We are facing erratic rainfall, melting glaciers, increased greenhouse gases, and a burgeoning population, which makes it increasingly difficult to locate fresh water where and when we want it. Do we have enough water? Well, 820 million people in 12 major river basins of India face high to extremely high water stress. per capita availability of water is expected to decline by 74% by 2025. And our total annual utilizable water resources, surface and groundwater, will only be about 1123 billion cubic meters. The average annual precipitation along with snowfall is about 4,000 billion cubic meters, of which 3,000 billion cubic meters is received in the monsoon season between June and September. Even though this appears to be a grim picture, actually we have enough water per capita if we distributed it better and avoided wastage. Enough for our need, but not for our greed, as Mahatma Gandhi has said. What must we do to improve water availability? I look at it as the 5 R's: retain, reduce, restore, reuse, recycle. To start with, let's look at retain. India has a very, very long history, 5,000 years of water management. The reservoir in Dholavira in Gujarat was set up between 3000 and 1800 BCE. And this was one of the locations of the famous Indus Valley civilization, which stretched across much of West India and what is today Pakistan. Sringaverapura near Allahabad was a location where Ganga floodwater harvesting was done 2,300 years ago. The Kallanai Grand Anicut on the Kaveri River, which was built by the Cholas 2,200 years ago, is still in use. And over the last several decades, almost 100 years, we've built a large number of dams, reservoirs, and water storage systems, including, as I have listed here, Hirakud Dam on the Mahanadi, Nagarjuna Sagar Dam on the Krishna, Bakra Nangal on the Satluj, Tehri on the Bhagirathi, and Sardar Sarovar Dam on the Narmada. But though we have been using these dams and impounding water in large reservoirs, we still face serious problems in going along this path. Why? Because dams are increasingly associated with displacement of local populations, deforestation, environmental degradation, and geological activity. It's not popular anymore to be building dams. There's a lot of opposition, and it's unlikely that we will easily be able to convince the populations in those areas, particularly local populations, particularly tribal populations, that it is necessary to do such violent damage to nature in order to build huge dams. And in addition, river flows are also decreasing due to demand and climate change. So for our increasing water needs, we need to revive and reinforce traditional water harvesting systems, which are highly efficient, simple, and eco-friendly. It's interesting to note that every region in the country has its own traditional water management technique, reflecting the geographical peculiarity, topography, and culture of the area. I'll run through some very quickly through these slides. The Kools are surface water channels in Himachal Pradesh. They carry water from the streams for irrigation. Ahar pines in South Bihar are reservoirs with embankments which catch the flow of flood water. And this is used for paddy harvesting, paddy cultivation in Bihar. The Khadins, which are earthen embankments built across hill slopes in Rajasthan. The Zabo of Nagaland, which are channels which carry rainwater from hilltops. And the interesting thing is that this rainwater is channeled through cattle yards, where they pick up manure and moves on to ponds on terraced hillsides. And from that, they thence to paddy fields. And in these paddy fields, it's not only paddy which is grown, but fish is also being cultured. And as a result, the manure is helping feed the fish as well as grow the crop. Check dams have been a very good way in which small interventions can manage to bring great results. Johad in Rajasthan, they're called Johads in Rajasthan, Mataka in Karnataka, and Temghara in Odisha. The Johads in Alwar district have been remarkable in through the Tarun Bharat Sangh of Rajendra Singh in bringing about tremendous change in raising the groundwater levels and changing the whole of the water situation and groundwater level situation in Alwar district and in neighboring districts. The Bandara in Maharashtra, in Nasik and Dhule districts, diverts water to the FUD, which is a community irrigation system on the rivers of the Tapi system. And this again is something which has been very beneficial to the cultivators in the area. Impounding water has always been an important factor in making sure that we have enough for drinking water as well as for agriculture. The pat and katta are bunds of stone and mud. You see these in Madhya Pradesh and also in the coastal areas. Basically, they hold the water for irrigation and prevent and minimize the flow of fresh water to the sea. Zings in Ladakh collect glacier water through a network of guiding channels, and this enables farming to be done in an area which otherwise has very little water. Tanks and percolation wells in Rajasthan are critical for drinking water. In particular, the Tanka is a system of rainwater harvesting through cylindrical pits in Rajasthan. The Par is enabling rainwater from catchments to percolate the sandy soil. And then, as you see, these quays are used to get the water from below, which has sunk into the soil. And the number of quays can depend on the size of the Par. We have water harvesting structures all across India. The big tanks, the Eri in Tamil Nadu, the Cheravu in Andhra Pradesh, the Dong in Assam. These are flood control systems. They also check soil erosion. They prevent wastage of runoff. They recharge groundwater. And in many cases, these tanks are interconnected. So they manage to move water from and distribute water from places of deficit to places of, from places of surfeit to places of deficit. So it is a means of ensuring that distribution can take place in addition to storage. The kunds in Haryana are saucer-shaped catchments which harvest water in a central circular underground well. And kunds are also in other parts of North India, and they are extremely useful both for drinking water and for irrigation purposes. Tanks and ponds across Maharashtra, there is the Ramtek model, which is an intricate network of ground and surface water bodies connected by underground and surface canal chains. The Nadi in Rajasthan, which of course Nadi also means river, but Nadi here is referring to village ponds which store rainwater from adjoining catchments in Jodhpur. Talab and lake, the designation of Talag, Sagar, Saman, lake, all these depend on the acreage of the surface water body. And so the small one acreage is the Talab. So you see here in the picture, the Talab in Suraj Talab in Mandu in Madhya Pradesh. We also have the large lakes, or the Sagar and Samand, which were built by kings for the public. The Bhojtal in Bhopal, which is on the top screen, top right screen, and the Lake Pichola in Udaipur, which is on the right bottom. A unique feature which you have in Gujarat, Rajasthan, even Karnataka are stepwells. These are tremendous improvisations for a time when we never had pumps, electricity systems to lift water easily. And so, and at the same time, by tapering it and enabling people to go down to the water, they managed to ensure that they would keep the water table at a position where it could be reached by people who could then carry the water up. The bowery has a similar arrangement. The Jalara in Rajasthan on the left, and the bowery in also in Rajasthan. The boweries were built very narrowly so that they could deepen the wells and minimize the water lost through evaporation. Other water storage structures, the Baolis, had beautiful arches, carved motifs, sometimes even rooms. They even had stages where they had dance performances in Firozshah Kotla, New Delhi, in Gujarat, in Rajasthan. The Panamkeni by the Wayanad tribe, Kuruma tribe in Wayanad, Kerala, used hard outer layers of stems of toddy palms, which were immersed in groundwater springs. These stored water, which were then used by the tribe. Conserving water in Andaman and Nicobar Islands and Arunachal Pradesh. In Andamans, the Shompen tribes used jack wells, pits encircled by bunds made of logs of hardwood. These were interconnected by split bamboo drains. And in Arunachal Pradesh, of course, much more recently, ferrocement tanks have been a low-cost alternative to masonry, plastic, and RCC, and have come up in a big way. Both these places are places where there's a lot of rainfall, and therefore using systems for capturing the rainfall has been very useful. As I mentioned in the beginning and subsequently here in this slide, what I wanted to show was that around 2,100 liters of rainwater can be harvested from 1 inch of rain if it falls from a 1,000 square foot roof. But and unfortunately, in India, only about 8% of our rainwater is actually harvested, which is very, very small. This is also something which our Prime Minister has made a mention of not too long ago. Swales or contour trenches are there. You put up these trenches along the contour so that when the rainwater comes down, it does not flow away, carrying away the topsoil with it, and it is impounded to be able to percolate into the soil through these trenches. The continuous contour trenches are being promoted across India now, and we have both NGOs and governments, state governments, which are pushing these in a very big way in Maharashtra, in Madhya Pradesh, in other states. And this has brought a lot of change to agriculture in villages, and they are making villages self-sufficient in water even in a year of drought. Along with this, of course, we also have recharge wells, which can add to the water supply in the groundwater table. The factor which is not really appreciated is the importance of groundwater to India. It is the main drinking water for our people. This is because most of our surface streams are polluted, contaminated. So it is groundwater which becomes the mainstay of our drinking water. 80% of our groundwater still is used for irrigation and about 8% for drinking. There is tremendous overexploitation of our groundwater, with over 20 million wells having been dug all over India. 67% of our irrigation is groundwater based. It is shocking that we are the biggest extractors of groundwater in the world, more than China and the USA combined. And India's irrigation efficiency is very low. 60% of all our water used for irrigation is lost. Industry needs to shift from groundwater. At the moment, industry is exploiting groundwater in a big way. Industry needs to shift from groundwater use to surface sources, and especially to the reuse of treated wastewater, which I will come to later in my presentation. And as I said from the earlier slide, continuous contour trenches, recharge wells, and soak pits can help to supplement groundwater. Afforestation, we have all given lip service to afforestation, and we don't realize how important it is in retaining runoff flows, reducing soil erosion, raising groundwater levels, mitigating flood damage, preserving biodiversity, and increasing flora and fauna, regulating the microclimate, and also in providing food and timber. I wonder if we can encourage every school child to plant 4 trees a year and try and see how that can make a change, because we need to plant millions of trees if we are to ensure that our forest cover does not go down, and if we are to ensure that we are able to preserve a good and healthy climate. Reduce. We need to be very conscious of the degree of waste we do to water, both water used in agriculture and water used in households, and also water used in industry. For agriculture, sprinkler and drip irrigation enables fertigation to be applied directly to the roots. This reduces water use by about 40%. We must avoid flood irrigation. I know that for 10,000 years, people have been growing rice with flood irrigation, but that does not mean that this is the best or most optimum way of doing things. There are enough examples shown by Israel in collaboration with Tamil Nadu Agricultural University and other places in India where they are growing rice with drip irrigation. And it has been a success, not only in terms of being able to do it, but in terms of increased yields. The system of rice intensification, which began in Madagascar and has shown that you can increase yields by 20 to 100% while reducing seed used, while saving water up to 50%. This is something which is increasingly becoming popular again in Tamil Nadu and some other states. But we need to see how to systemize this. Basically, the old system of having clutches of large numbers of seedlings of rice being planted in one spot on a small hill, that is avoided in this, and we have single or double rice seedling being planted in a array which is pre-planned. So this enables not only reduction in the number of seedlings, but actually increases the yield. And this can also be used, though it's called system of rice intensification, it can also be used for growing of things like lentils and dal. Once upon a time, we used to be huge producers of dal. Today, we are importing dal. So we need to know how we can increase dal. Punjab is today growing rice instead of dal, because since 2000, it has seen the availability of minimum support price, the availability of being able to get money for this has resulted in our having huge backup storage of rice, cereal, grain in our warehouses where it's eaten by rats, and where now we are thinking of exporting it all over the place. Instead, we should incentivize farmers to grow lentils as the second crop instead of growing rice in places like Punjab, if we are wanting to make sure that the production is optimal, and also to make sure that water use is reduced. We need to select crops according to the water availability in water-stressed areas. We need to shift from rice and sugarcane to less water-intensive crops like millets and bamboo. This will enable us to reduce virtual water consumption. In the future, we will all be talking about virtual water consumption. Since 1 kilogram of rice uses 2,800 liters of water, 2,800 liters of water, you're talking about, if you sell 1 million tons of rice to some other country, you're actually exporting 1 trillion liters of water. 1 trillion liters. So you need to be conscious that this is a terrible use of your what you have in hand, and this needs to, we need to have a rethink of this way of doing things. So we also need to reduce freshwater consumption by rich city dwellers. I do not say this for all people. Many Indians are having to do with 20 to 70 liters per capita per day, but rich Indians are still wasting water, washing their cars with hoses. In the USA, which is the most wasteful nation in terms of water consumption, you have 570 liter per capita per day. The UK is 150. India recommends between 100 and 150, but 70 is also seen as a figure popularly used in India, 55 to 70. But we really need to ensure that wherever water we have, we manage to conserve it and we manage to use it well. What are the innovative technologies we have to reduce water use? Over 60% of municipal water is lost daily in cities and towns due to leaks, open or broken taps, theft, and neglect. Now, these technologies I am talking about, distant meter reading, these all exist already. Some of them are from countries like Israel, but they are also available now across the world and in India. Distant meter reading technology will enable us to know without having to physically go and check. Sensors can monitor quality and quantity. The use of big data, which will check water flow to a given neighborhood, conditions when a pipe is likely to burst, temperature, and thousands of other inputs to develop a profile to detect anomalies that are often predictive of a leak. And then, of course, robotic cameras to check the inside of sewer pipes to check for leaks in advance. Restore. I've given here a picture of a typical water treatment plant. Unfortunately, we have very, very few of these in India. And this is a basic water treatment plant where you do sedimentation, filtration, disinfection. When I wish to throw this question to the listeners, when can we drink water straight from our taps again? I used to do this till 1982 in Delhi. But today, I don't think I would do it in any place in India. It's sad. It's really sad that we have ruined our water supplies to such an extent that for every drop of water, we need to depend on a filter, an aqua guard, or whatever it is to be able to get water to drink. We need more water treatment plants, which is something which is really in shortage. Parts of India have arsenic poison in water, heavy metals, fluorides in water. So we need to have technologies in place. These are not expensive technologies. These already exist. And it is the responsibility of any municipality to ensure that these are removed. Upstream wastewater becomes downstream drinking water source. I wish people would remember this when they throw their waste without processing into the rivers. India is ranked 120 out of 122 in water quality, which is not something we can look at with pride. We need to use IT to monitor water quality at the panchayat, tehsil, and district levels. So that, and this is all very possible today with information technology, with core dashboards, with the capacity for a district collector to monitor everything that goes on in his district in terms of water. Atlantium and Sodis. Atlantium is basically this tube which you see on the top of the presentation. The tube has got ultraviolet light in it, and when the water passes through the tube, disinfection of the water takes place. Sodis does a similar thing, but it's the Indian Jugaad system where the bottle is, a clear bottle is used and sunlight, UV from sunlight is used. Solar distillation and clay filtration, I've just given an example in this picture for remote rural areas, is something which we can easily manage to provide. Over and above everything, industry must operate on a polluter pays principle. Industry cannot get away. We see that there is change. For example, in Kanpur, the tanneries have been brought to book, and a lot of them have changed. They are now recovering the cadmium and other heavy metals that they were earlier throwing into the water. But all industry must operate on a polluter pays principle if we are to ensure that there is water for all. I've just shown here a picture of traditional water filters, biochar. Biochar is an excellent water filter, and using charcoal, that is biochar, biosand, and sand and gravel, you can make excellent filters which can do most of the filtration, even in areas which do not have much affluence. Reuse. This is a shocking thing which I discovered, that India has 816 sewage treatment plants, of which only 522 are functional. The USA has 14,000, I'm getting my screen blocked. I think it's 14,748, yes. So it's a huge difference. We must remember that the US is 1/4 the population of India and 3 times the size. So they are occupying 12, we are 12 times denser than they are. Yet this is the situation where we have so few sewage treatment plants and they have so many, 14,700 versus 816, actually 522. Ideally, we should have 1 sewage treatment plant for every 100,000 population. And I've just given here for information kind of the typical sewage treatment plant. We must reuse wastewater. It's a huge resource which we're just throwing away. India generates 62,000 million liters per day of sewage. Only 30% of that is treated. 43,167 million liters per day of untreated sewage is directly thrown into our rivers, into water bodies, or the sea. This is an untapped resource. We don't realize that sewage is not waste. It is a resource which can yield valuable fertilizer and energy, power from methane gas. Water for irrigation and industries, including power generation, could be met from treated wastewater. Treating wastewater to freshwater quality is half the cost of desalination systems and does not have the issues of brine damaging marine ecosystems. And many countries are already reusing treated wastewater. Israel is an example of one which uses 94% of its wastewater. Australia, Singapore uses almost all its wastewater. The US also does, though to a much lesser extent. I have not understood why even when plants in Bombay, where close to where I live, there is a sewage treatment plant. That plant releases the treated water back into the sea without doing anything about it. And when I asked them, they said that the farmers don't want sewage water for farming. This is ridiculous because the NPK resource in sewage would be hugely advantageous to crops once the pathogens are removed. But we need to educate people. We need to have more of since the proper sewage treatment plants are expensive, require power, and are not easy to maintain. We need simple, cost-efficient structures like constructed wetlands. I've written here, for example, that Denmark has one for 5,000 people. We may not achieve that, but even if we do 1 or 2 magnitudes higher, we still would be better off than we are today. Israel's Mapal uses a system where they have a diffuser which shoots air bubbles downwards and provides oxygen to enable bacteria to eat up pollutants and clean the water. That bacteria is actually producing electricity, and that is used to power the sewage plant. These are the kinds of innovations which we need to get and put on in our systems here in India. This is a more passive system of wastewater treatment, facultative lagoons with stabilization ponds, where basically you use natural phenomena and bacterial oxidation of organics by photosynthesis, by algae, and by wind. And the carbon dioxide released by bacteria is used by the algae, so it's a symbiotic relationship. And you have excess biomass and settleables treated by anaerobic bacteria. Recycle, this is the 5th of my things. I think timing-wise, I'm okay, isn't it? I think so. We come to desalination. 97.2% of all the water on our planet is seawater, saline. India is in a particularly lovely position because we have 300 days of sunshine and high ambient temperature. We have 7,500 kilometers of coastline. So we have a tremendous opportunity for putting in smaller solar thermal desalination and distillation units, which could provide water, especially in coastal areas. As I said earlier, desalination should be the last option. When you have finished all the earlier 4, which I mentioned, if you still don't have water, then you come to desalination. But it can happen and does happen that you may still require to put in place this. And multi-effect plate evaporators, incidentally, these are also used on ships. They use only 2.5 to 2.7 kilowatt hours per 1,000 liters of fresh water, which is 30 to 70% less than reverse osmosis. And these kind of units could be game changers in terms of bringing in solar desalination systems in India. I've just highlighted briefly the desalination technologies available to us. Reverse osmosis is most widely used, but we must remember that it is capital intensive, energy intensive, and though costs have been reduced significantly with better membranes, it still requires pre-screening, pre-treatment to prevent biofouling. The brine effluent, what you push out of the system, is equal to the amount of fresh water that you're putting in. In other words, if you are putting in 200 million liters a day, you are pushing out 100 million liters a day. So, and you get 100 million liters of fresh water, 100 million liters of brine water. So it is an extremely inefficient system in that sense, especially because at the moment, the system used in Chennai and most other places is of directly leading a pipe into the sea and disposing of the brine. This causes grave harm to marine ecology. The alternative is to go in for thermal desalination using multiple effect distillation and with thermal vapor compression, and also multiple, as I mentioned earlier in my earlier slide, multi-effect plate evaporators. These are less capital intensive, they use less energy per volume of water, they're very attractive, where waste heat from industry or solar energy is available. They're more eco-friendly, as you can manage to extract much of the water. So it's not as if you're doing 50-50 like in RO. You have a potential for avoiding discharge altogether through zero liquid discharge systems, where you use evaporators, vaporizers to enable recovery of salts. This is being done in California and other parts of the world, and is quite successful in recovering salts of sodium, of course, our famous table salt, but also of potassium, calcium. You get gypsum, which is used in the construction industry, magnesium. These are all available and could offer additional revenue in addition to giving you water for consumption. When nothing else is available and all else fails, as they say, turn to the air. There is more water in the atmosphere than in all rivers on earth. And this water is clean, it is TDS and bacteria-free water. And so it is tremendous. The only problem with it is also one of the most expensive waters, but the expense can be brought down significantly if you use solar systems for harvesting the water. Ecolo Blue is a company in Abu Dhabi, which has an air water generator, which condenses about 400,000 liters per day in desert-like conditions. If Ecolo Blue were used in Mumbai or Chennai, it would do almost 50% more, if not more, than what it is doing in Abu Dhabi because of the relative humidity in the atmosphere. Watermaker India has successfully installed air water generators in Andhra Pradesh. Meghdut is a Maitri Aquatech plus CSIR, Indian Institute of Chemical Technology tie-up, which proposes to install air water generators in defense installations, hospitals, railway stations across India. They are also, I think they are proposing, or they have already exported to South Africa and some other countries. We can, and I have checked this out with mathematical working out, we can produce water at 2 rupees per liter using 0.3 kilowatt of power. This is what Meghdut advertises. Grid, solar, wind, and oil. You have all the options for what type of power you want to use. The additional interesting thing about this, because these are small compact units which you can move around, they are very useful for small communities and in emergencies and disaster management systems. So I come to the end of my, the conclusions that I want to show you in this talk. I think 40, well, just about. The steps to be taken include retain water by reviving traditional water systems across India, undertake extensive afforestation because this itself will hold water. It will be doing the work that you want to do, especially in Abadi and wastelands. There are millions of hectares of Abadi and wastelands in different different parts of India. And it is a huge amount of land which is available, which potentially could be afforested, not just for water harvesting, but also can produce the benefits of forest produce. We need to make water a central subject. We need to enforce regulations for groundwater extraction and for surface water use. And though I know this will be politically very unpopular, we need to pay for the use of water for irrigation. No free water. There is no such thing as a free bill for water. reduce water use through the use of drip irrigation, more efficient irrigation systems, initiatives like system for rice intensification, less water intensive crops, reducing leakage and wastage, and the metering of water. Enforce the polluter pays principle to restore drinking water supplies. IT dashboards at district, tehsil, and panchayat samiti levels, as I mentioned earlier, can monitor water quality. Build many, many more sewage treatment plants, facultative lagoons, constructed wetlands. I'm happy to see that you have a constructed wetland in IIT Gandhinagar. To promote reuse of wastewater. This would likely fulfill our needs without going to the next stage, which is, if still more water is required, recycle it through desalination of seawater or brackish water, or employ air water generators to extract water from air. I thank you very much. It has been a pleasure, and I look forward to your questions and comments.